I hinted at this in, I think it was in the last video. The next thing that we're going to look at is a crossed Claisen condensation. And this is when we're using two different esters. Just like a crossed aldol reaction. And just like with the crossed aldol reaction, we do have the potential for making up to 4 total products of the reaction. When we were looking at this with the aldol reaction, remember I said you could have A attacking B, or you could have B attacking A, or you could have A attacking another A, or you could have B attacking another B. So you can get up to 4 different products, not thinking about stereoisomers. And that's really a bummer in the lab. So it is best if we do the same thing we did with the aldol reaction, best if we start by converting one of the esters to its enolate. We're going to use the same thing, LDA. And then once we get that ester converted to the enolate, then we can add ester number 2. And this will hopefully mean that we only have the first ester attacking the second ester and no other options. Another option that we have for controlling a crossed Claisen reaction, and this is also one that we would have with an aldol reaction as well, if one ester has no alpha hydrogen, has 0 alpha hydrogen. If it has hydrogen, if it doesn't have any alpha hydrogen, it can never be turned into an enolate, which means that it can only be attacked. It can't be an enolate. In order to become an enolate, you have to have one of your alpha hydrogen removed. So if one of the esters doesn't have any alpha hydrogens, it can't be an enolate, and it can only get attacked. And that's also going to help us minimize the number of byproducts that we might have in the reaction. So let's take a look at some examples of crossed Claisen condensation reactions. So here is one. I think we have 2. No, we only have 1. Here is one, and these are 2 different esters, but even though we have 2 different esters, notice that we have the same OR group all the way through, matching, matching, matching. And so when we're looking at a crossed Claisen reaction, the first thing that we should look at is where are the alpha hydrogens in these 2 esters? So here's the alpha carbon in the first ester, and that alpha carbon has 4 bonds on it, which means it doesn't have any hydrogens there, which means it cannot become an enolate. For the other ester, here are its alpha hydrogen, and those are the only alpha hydrogens that we have available to us, so those are the ones that are going to end up getting removed. And here is the structure of that enolate. And that enolate is then going to attack the other ester's carbonyl group. And the product that we get from that, I'm going to draw that ester with its carbonyl group opened up because it just got attacked. I better put some numbers on these carbons. I'm going to make that one carbon number 1. It's carbon number 1, and I'm going to make this one 2 and 3. And so this is carbon number 1. That's the one that got attacked. Carbon number 1 got attacked by carbon number 2, so we created a bond from 1 to 2. Carbon number 2 has a benzene ring on it. Carbon number 2 also has carbon 3 Carbon 3 is the carbonyl and the OCH3 group. So there it is. Next thing that happens here is that O- comes back down and recreates the carbon-oxygen double bond. And let's draw what we get from that. There, that was carbon number 1, and I just drew carbon number 2. Carbon number 2 has the benzene ring on it up to carbon number 3. So there is our product. Really, I'm pretty sure that is wrong. I made a mistake. Carbon number 2. Back it up, is connected to a benzene ring. It is not part of a benzene ring. It is connected to carbon number 3, which is part of the carbonyl group in the ester. That looks better, much better. So now what do we get? We have 2 with the benzene ring coming off of it, 3 OCH3. 1, 2, 3. There it is. Now then, before we move on with this mechanism, the next thing we're going to do is look at that double E alpha carbon, and do we have any hydrogens on it? We sure do. So that OCH3 group that we got rid of when we recreated the carbon-oxygen double bond, that thing is going to grab that alpha hydrogen and pull it off. And it gives us this enolate. And we're going to protonate the enolate with some acid and put that hydrogen right back. Just like that, and there's our product.